Okay, hello AP Stats students. Um, you have received a packet and you're going to follow through um, with the video and writing in your packet. And then when you get done with the video, you can work on homework 7. Really, what I really want to cover is geometric probabilities. So we're going to start with geometric and then we'll come back to these examples. So we're going to kind of just skip this page and we're going to skip this page just for now. And we're going to start here. That way, if all you need is to learn geometric, you can just do this at the beginning of the video and then be done. And if you need a little bit more help with binomial, I'll go back and do those first few slides. Okay, so to get you to understand what geometric is all about, this is my first example. It says Barney is making phone calls to get people to go to a laser tag convention this weekend. Historically, there's a 30% chance that he is successful when he calls someone to go. He's going to call until he gets the first success and find someone to go. I hope you understand this reference. This is from a very popular TV show. So my question is this binomial? So can we check off each of these bins? So we're going to start with B for binary. Do we have a success and do we have a failure? Well, he's trying to call people to go to the laser tag convention. So a success would be if someone wants to go with him, and a fail would be if they don't. So that checks off. Then I is independent. Is each trial independent? So a trial is a phone call. So yeah, I guess I would say that each phone call is independent of the other phone calls. N, number. Is there a fixed number of trials? Does the description up here say that he's going to call a certain amount of people? It says he's going to call until he gets the first success. So it does not indicate a set number. So this is not, that condition is not met. S, for probability of success, there is a probability of success, that's 30%, so that does check off as well. But since the N in bins does not work, then it is not binomial. So what happens is this is actually a geometric probability question. Geometric follows the same kind of setup as binomial, except the only thing that's different is the N. There's no set number. In this case, you're just going to go until you get your first success. So the N is what's different. There's no set number. You're just going to keep going and going and going and going and going until you get a success. Otherwise, the B, the I, and the S all work. So when you know something is geometric, we're only going to deal with two kinds of probabilities. We're going to look at the probability that your first success is on a certain trial. And there is kind of this formula, even though this formula is not on your formula sheet. But if you understand kind of how it works, then you won't really need the formula. So the idea is, if I'm trying to find a first success on the nth trial, then that means I've failed every other trial up until the success. So here is the success. On the last trial, there's only one success, and then the rest is a fail. So these are fails on all the other trials. So we've succeeded once on the last trial, and then we failed every time before that. I know I spelled success wrong, but the pen is too hard to write, so I'm not going to fix it. Okay, the next one is when you have a probability of a success and it takes more than n trials to get a success. So the problem with this is I don't know when the success happened. I just know that it took more than n number of trials. So because I don't know when the success happened, all I know is that I've failed n number of trials. So that's what this is representing. So we only know we failed that many times. I don't know when the success happened. Okay, it's going to make more sense if we do an actual example. All right, so in this example, Rita has a really bad lawnmower, and she never really knows when it's going to start. On any particular pull, the mower has a 20% chance of starting. So there is a success. We get the mower to start. There's a fail. It won't start. Each pull is independent. There's no set number of pulls, though. Nowhere does it say she's going to pull the mower cord, a certain amount of times. There is a probability of success, though. It's right here, 20%. So this is geometric because there's no set number of trials. If we want to find the probability that it takes her exactly 3 pulls to start the mower, okay, then this is how I would write it out symbolically. It takes her exactly 3 pulls. Well, if it starts on the 3rd pull, what happened the first 2 times? So it failed the first 2 times. If the probability of it starting is 20%, then the probability of it failing would be 0.80. And that would be to the 2nd power because it failed twice. And then she had a success. And this is, oh my gosh, this board is so hard to write with sometimes. She only had 1 success. It happened to be on the 3rd chance, but it was only 1 success. So that's why it's to the 1st power. So she failed twice and then got a success. And then you could type that in your calculator and get the actual answer. For part B, find the probability that it takes her more than 10 pulls. Okay, more than 10. I don't know when the mower started. It could have started on the 11th pull. It could have started on the 20th pull. I have no idea when it's going to start. All I know is that it takes more than 10. So that means that it failed 10 times. It failed the first 10 times. We know that for sure. So we're going to do the probability of failing, 0.80, to the 10th, because we know that. That's as much as we know. Oh my goodness, I can't get it to write. There. So it failed the first 10 times. We know that for sure. I don't know when the success happened. This is all I can say. And then you can type that in your calculator and get your answer. All right, here's my last geometric example. Mr. Bowler loves to go bowling. On any particular frame, the probability he gets a strike is 15%. So a success is a strike, a fail is anything else. Each time he rolls or rolls the ball, that is independent. But there's no set number of times he's going to roll the ball. There is a probability of success, though. So if we're checking bins, the B works, the I works, and the S works. Hang on. And the S works, but the N does not. So it's geometric. So what's the probability that he gets a strike on the 10th frame? So what's the probability that he gets a success on the 10th frame? Well, what happened the first 9 frames? He failed. He did not get a strike. So what's the probability of failing if the probability of success is 15%. Then the probability of failing would be 0.85. If he gets a strike on the 10th frame, then that means he failed the first 9 frames. So it's failing to the 9th power. And then he gets a success. Just one success. Okay, and then you could type that in your calculator and get the right answer. For part B, what's the probability that it takes him more than 5 frames before he gets a strike? So the probability that it takes more than 5. So I don't know when the strike happened. I don't know which frame the strike happened. All I know is that the first 5 frames he did not get a strike. So the first 5 were a fail. So it'll be 0.85 to the 5th. That's all I know. Type that in your calculator and get your answer. So that's geometric. You kind of just have to logic your way through it. Even though there are these formulas here, those formulas are not on your formula sheet. So you either have to memorize them or you have to kind of just think about the problem. What happened the first n number of times, and then what happens? So if that's all you need, then go ahead and do homework 7. Otherwise, if we go back to the very beginning, we'll do some more binomial questions real quick. So here, suppose the probability of getting a bullseye playing darts is 0.37. We're going to throw 25 darts and count the number of bullseyes. So is this binomial? Do we have a success? Yes, a success is getting a bullseye and a fail is not. Is each throw independent? Yep. It says the trials are independent. It says each throw is independent. Do we have a set number of trials? The set number of times we're going to throw? Yep, it says 25 times. And then do we have a probability of success? Yes. It said up here that the probability of getting a bullseye is 0.37. So this is binomial. How many bullseyes would we expect to get? Well, expect is the key word. Expected value is the mean. So we have the formula for the mean. It's mu equals NP. N is the number of trials, which is 25. And P is the probability of success, which we're told is 0.37. So just multiply those together and you get your expected number of bullseyes. So let's see what that is. 25 times 0.37. We get 9.25. So in 25 throws, I would expect to get 9.25 bullseyes. What's the probability we get 12 bullseyes exactly? So the probability that we get exactly 12 bullseyes. This is binomial, remember, so we get to use our binomial formula. So the top number is the number of trials, 25. The bottom number is the number of successes we're trying to get, which is 12. Then we take the probability of success, which is 0.37, and we raise that to this bottom number, 12. And then we do the probability of failing, which is 1 minus 0.37, which is 0.63. And that will get raised to the 25 minus 12, which is 13. And then in your calculator, you're going to do menu 65, and you're going to look for binomial PDF. And then it'll ask you for the number of trials, which is 25. It'll ask you for the probability of success, which is 0.37. and it'll ask you for the x value, which is 12, and then you'll get your answer. Okay, this is the last page. What's the probability that we get less than 10 bullseyes? So, less than 10 means we're going to start and go from 0 up until 9 because it's strictly less than 10. So when you go to type it in, your lower bound will be 0 and your upper bound will be 9. Make sure you show the first term, the next term, and then dot, 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 the last term. For part B, what's the probability we get at least 13 but less than 20? So at least 13 means 13 or more, but then strictly less than 20. So you should have an equals to here, but not here. So your lower bound will be 13, but your upper bound is going to have to be 19 because it can't actually equal 20. Let me get my pen. Okay, so here's the lower bound of 13, the upper bound of 19. For the last one, what's the probability that we get more than 8? So strictly just more than 8. Then our lower bound is going to have to be 9. And it's going to go all the way up to 25 because that's the highest we can go. We're only throwing it 25 times. And there's the answer for that one. Okay, so give homework 7 a shot, and I will see you on Monday. Have a great weekend.